Hello there, and welcome. Tonight I want to take you somewhere special, somewhere beyond the gentle glow of your bedside lamp, beyond the soft rustle of your sheets, beyond even the quiet hum of the world outside your window. I want to take you to a place where the universe reveals one of its most beautiful mysteries, a place where spinning wheels of cosmic matter meet the steady river of time, where rotation and flow dance together in the darkness between stars. Settle in, make yourself comfortable, and let your breathing slow as we begin this journey together, you and I, into the heart of a question that has puzzled humanity since we first looked up at the night sky and wondered why everything turns, yet time only moves forward. It's a question that seems to contradict itself at first, doesn't it? Space turns and wheels and spins in countless directions, from the gentle rotation of our Earth that brings you sunrise and sunset, to the majestic spiral of galaxies turning like cosmic pinwheels in the void. And yet time, mysterious time, only flows in one direction, from past through present into future, never backward, never sideways, always forward like a river that knows only one way to the sea. But what if I told you that this apparent contradiction is actually one of the most profound harmonies in nature? What if the universe's many spins and time's single arrow are not opposing forces but complementary dancers in a cosmic ballet so vast and beautiful that we can only glimpse its edges from our small corner of existence? Before we go deeper into this mystery, I'd love to know where you're listening from tonight. Are you tucked into bed in a bustling city where the lights never quite go out? Or perhaps you're in a quiet countryside where the stars shine bright and clear? What time is it where you are? Is it late evening with the day's last light fading from your window? Or have you already crossed into those small hours when the world feels hushed and still? If you'd like, leave a gentle comment below, whisper your location into our shared space. And if this journey soothes you, if these words help carry you toward peaceful sleep, perhaps you might like this video and subscribe to join us for more voyages into the cosmic mysteries. There's no rush, no urgency, just a quiet invitation to become part of our community of dreamers and wanderers who find peace in contemplating the vast and beautiful universe we call home. Now, as you settle deeper into comfort, perhaps adjusting your pillow just so, letting your shoulders release any tension they've been holding, I want you to imagine something with me. Imagine that you could step outside of time for just a moment, that you could hover above the flow of existence and see it all at once. What would you see? You'd see galaxies spinning like dancers frozen mid-twirl. You'd see planets tracing their patient orbits. You'd see moons circling worlds, and if you could look close enough, you'd see atoms themselves, with electrons in their quantum dance around nuclei. Everything spins, everything rotates, everything turns in this universe of ours. And yet, through it all, time flows in just one direction, carrying everything forward, never back, like a cosmic river that knows no reverse. Scientists have been studying this phenomenon for generations, and what they've discovered is both humbling and magnificent. When we look out into space with our most powerful telescopes, when we peer into the cosmic microwave background radiation that is the afterglow of the Big Bang itself, we see evidence of rotation everywhere. Galaxies spin, typically making one full rotation every few 100 million years. Our own Milky Way, this island of stars we call home, completes a full turn every 225 million years or so. That means that since the Earth formed 4.5 billion years ago, our solar system has made only about 20 complete trips around the galactic center. Just 20 laps around our cosmic neighborhood in all that time. It makes you realize how vast these scales really are, doesn't it? But here's where it gets even more interesting. While everything in space seems to spin, the universe as a whole, as far as we can tell, does not rotate. When scientists study the cosmic microwave background, the ancient light from when the universe was only 380,000 years old, they find it's remarkably uniform in all directions. If the entire universe was spinning like a giant cosmic carousel, we would see patterns in this ancient light, distortions that would tell us which way the universe turns. But we don't see that. Instead, we see a universe that appears the same in every direction, what scientists call isotropic, like looking at a perfectly still pond that reflects the sky equally in all directions. This brings us to one of the most profound realizations in all of cosmology. While the contents of the universe spin and wheel and dance, the stage itself, the fabric of space-time, appears to be still, or at least not rotating in any detectable way. It's as if the universe is a vast theatre where countless dancers perform their spinning choreography, but the theatre itself remains motionless, providing a stable stage for all this cosmic motion. And through this still stage flows time, always forward, never backward, carrying every dancer, every spinning galaxy, every orbiting planet, every one of us toward tomorrow. The question of why time flows in only one direction, while space allows rotation in any direction, is connected to one of the deepest principles in physics, something called the second law of thermodynamics. Don't worry, I won't burden you with equations or complex mathematics. Instead, think of it this way. Imagine you have a sandcastle on a beach. That sandcastle represents a state of low entropy, a state of order and structure. Now, imagine the tide coming in. The waves wash over the sandcastle, and grain by grain it dissolves back into the smooth beach. The sandcastle never spontaneously reforms from the smooth sand. The waves never run backward to carefully rebuild what they destroyed. This is entropy in action, the tendency of the universe to move from order toward disorder, from structure toward smoothness, from low entropy toward high entropy. This increase in entropy is what gives time its arrow, its direction. The early universe started in an incredibly special state of very low entropy, like the most perfect sandcastle ever built, and ever since that moment, 13.8 billion years ago, entropy has been increasing, and this increase is what we experience as the forward flow of time. Every moment that passes, every breath you take, every thought that crosses your mind, adds a tiny bit more entropy to the universe, pushes time's river forward just a little bit more. You are, in a very real sense, helping to drive time forward just by existing, just by being here, listening to these words, letting them wash over you like gentle waves. But why doesn't this arrow of time affect rotation? Why can things spin clockwise or counterclockwise with equal ease, while time stubbornly refuses to flow backward? This is where the mystery deepens, where we enter territory that even our best physicists are still exploring. You see, the laws of physics that govern rotation are what we call time reversible. If you filmed a planet orbiting a star and played the film backward, the backward version would look just as physically possible as the forward version. The planet would simply appear to be orbiting in the opposite direction. But if you filmed an egg falling off a table and breaking, the backward version, where the egg spontaneously assembles itself and jumps back onto the table, would look obviously wrong, obviously impossible. This is the difference between reversible processes like rotation and irreversible processes that give time its arrow. As you lie there, perhaps feeling yourself beginning to relax more deeply, consider this beautiful fact. You are made of matter that has been spinning for billions of years. The atoms in your body, the carbon in your muscles, the calcium in your bones, the iron in your blood, all of these were forged in the hearts of stars that were themselves spinning as they burned. When those stars died in spectacular supernovae, they scattered these elements into space in great spinning clouds that eventually condensed to form new stars, new planets, and eventually you. You are literally made of cosmic spin, assembled from matter that has been turning and wheeling through space for eons. And yet, despite being made of all this spinning matter, you experience time in only one direction. You remember yesterday but not tomorrow. You can look at old photographs but not future ones. You age in one direction, from young to old, never the reverse. This is the profound asymmetry at the heart of existence. Space treats all directions equally, allowing spin and rotation in any orientation, but time plays favourites, choosing one direction and sticking to it with absolute determination. Let me share something fascinating that scientists have discovered about the relationship between spin and the structure of the universe. When we look at galaxies across the cosmos, we find that they don't just spin randomly. There are subtle patterns, faint correlations in how galaxies rotate relative to the large-scale structure of the universe. Galaxies that live along the same cosmic filament, those vast threads of matter that connect clusters of galaxies like a cosmic web, often show slight preferences in their spin directions. It's as if the universe has a very gentle, very subtle form of choreography, where neighbouring dancers tend to spin in harmony with each other. This cosmic choreography emerges from something called tidal torquing. In the early universe, when matter was just beginning to clump together under gravity's patient pull, regions of slightly different density would exert gravitational forces on each other. These forces, though weak, would cause nascent galaxies to begin rotating, like how a gentle breeze can set a weather vane spinning. Over billions of years, these initial tiny rotations would amplify, eventually producing the spinning galaxies we see today. It's a process of incredible patience, where the universe takes billions of years to teach matter how to dance. The Sloan Digital Sky Survey, one of the most ambitious attempts to map the universe, has catalogued the positions and properties of millions of galaxies. When astronomers analyze this vast dataset, they find these subtle spin correlations extending across millions of light years. It's as if the universe has a memory of its early conditions encoded in the spins of galaxies, a kind of cosmic DNA that tells the story of how structure formed from the smooth, early universe. And all of this happens while time flows steadily forward, never pausing, never reversing, carrying all these spinning galaxies toward their future configurations. Think about your own experience of spin and time right now. As you lie there, you're spinning with the Earth at hundreds of miles per hour, though you feel perfectly still. You're orbiting the Sun at 67,000 miles per hour, though you have no sensation of this incredible speed. You're wheeling around the galaxy at 500,000 miles per hour, and the galaxy itself is moving through space at even greater speeds. You are, at this very moment, participating in a cosmic dance of incredible complexity and beauty, layers upon layers of rotation and movement, and yet, through all of this motion, time for you flows at its steady pace, second by second, moment by moment, breath by breath. There's something deeply comforting about this, isn't there? No matter how complex the universe is, motions, no matter how many ways matter spins and wheels through space, time provides a steady rhythm, a reliable beat that underlies everything. It's like a cosmic metronome that keeps all of existence in sync, ensuring that causes precede effects, that stories have beginnings, middles, and ends, that life can unfold in meaningful sequences from birth through growth to rest. Scientists have discovered that even time's flow isn't perfectly uniform throughout the universe. Einstein's theory of relativity tells us that time flows at slightly different rates, depending on gravity and motion. Time moves a tiny bit slower at your feet than at your head, because your feet are closer to Earth's gravitational center. Time moves slower for someone traveling at high speed relative to someone at rest. GPS satellites have to account for these tiny differences, adjusting their clocks to stay synchronized with Earth's surface. But even these variations in time's rate don't change its direction. Whether time flows quickly or slowly, it always flows forward. This brings us to one of the most mind-bending aspects of modern physics. When scientists study the fundamental equations that govern the universe, from Newton's laws to Einstein's relativity to the equations of quantum mechanics, they find something remarkable. Most of these equations don't actually specify a direction for time. They work just as well backward as forward. It's only when we add the second law of thermodynamics, the law of increasing entropy, that time acquires its arrow. In a very real sense, the direction of time emerges from statistics, from the overwhelming probability that entropy will increase rather than decrease. Imagine shuffling a deck of cards. If you start with the cards in perfect order, ace through king in each suit, and shuffle them, they'll become disordered. You could shuffle them for a lifetime, and they'd almost certainly never return to that perfect initial order. Not because it's physically impossible, but because it's so incredibly improbable. There's only one way for the cards to be perfectly ordered, but there are billions upon billions of ways for them to be disordered. This is why entropy increases, why time flows forward, why we remember the past but not the future. As you continue to relax, perhaps feeling your breathing becoming slower and deeper, consider how this connects to the spinning motions we see throughout the universe. Each spinning galaxy, each orbiting planet, each rotating star is like a cosmic clock, marking time through its rotations. But unlike our earthly clocks that tick in discrete seconds, these cosmic clocks turn smoothly, continuously, their rotations blending seamlessly into time's forward flow. The Earth's rotation gives us days, its orbit gives us years, the Moon's orbit gives us months, and all of these cycles nest within each other like Russian dolls, creating the complex rhythms of time we experience. But there's something even more profound happening here. The universe's expansion itself provides a kind of cosmic clock, a universal measure of time's passage. Since the Big Bang, space itself has been expanding, stretching like a vast three-dimensional fabric, carrying galaxies apart like raisins in rising bread dough. This expansion provides a cosmic timestamp for everything that happens. When we look at distant galaxies, we see them as they were billions of years ago, because their light has taken that long to reach us. We're literally looking back in time, seeing the universe's history written in light across the night sky. This expansion of space is accelerating, driven by something we call dark energy, a mysterious force that makes up about 68% of the universe's energy content. We don't really understand what dark energy is, but we can measure its effects. It's causing the expansion of the universe to speed up over time, pushing galaxies apart faster and faster. In the far future, trillions of years from now, this acceleration will have carried most galaxies so far apart that they'll no longer be visible to each other. Each galaxy will become like an island universe, alone in an empty sea of space, still spinning but isolated, still marking time but with no one else to share it with. But don't let this far future scenario trouble you. We're talking about timescales so vast that they dwarf human comprehension. The universe is only 13.8 billion years old, and it will be hundreds of billions of years before these isolation effects become significant. For now, and for countless generations to come, we live in a universe rich with visible galaxies, rich with spinning matter, rich with the complex interplay of rotation and time's flow. We live in what you might call the universe's golden age, when stars still shine brightly, when galaxies still dance together in groups and clusters, when the cosmos is alive with activity and change. Let's return to that fundamental question. Why does the universe spin in one direction, but time only flows in another? Part of the answer lies in the different nature of space and time themselves. Space is three-dimensional, offering countless directions for rotation. You can spin around a vertical axis like a figure skater, around a horizontal axis like a gymnast, or around any axis in between. The three dimensions of space provide infinite possibilities for rotational motion, but time is one-dimensional, a single line extending from past through present to future. There's only one direction to go along a line, forward or backward, and the universe has chosen forward. Some physicists have speculated about whether there might be regions of the universe where time flows backward, where entropy decreases rather than increases. These would be regions where broken eggs reassemble, where coffee unmixes from cream, where stars absorb light rather than emit it. But we've never observed such regions, and there are good theoretical reasons to believe they don't exist, at least not in our observable universe. Time's arrow appears to be universal, pointing the same direction everywhere we look. There's a beautiful symmetry in how rotation and time work together to create the patterns we see in the universe. Rotation tends to create structure, from the spiral arms of galaxies to the rings of Saturn to the double helix of DNA. Time's forward flow allows these structures to evolve, to change, to tell stories. Without rotation, the universe would lack much of its beautiful structure. Without time's arrow, that structure could never develop, never change, never give rise to the complexity we see around us, including life itself. Think about water going down a drain. It spirals, creating a little whirlpool, a miniature galaxy of water. The rotation is caused by the Coriolis effect, a consequence of Earth's spin, combined with any slight asymmetry in how the water starts moving. But the water only flows one way, down the drain, never up. This simple example captures something essential about our universe. Rotation creates pattern and structure, while time's arrow ensures that things happen, that change occurs, that stories unfold. In the quantum world, the world of atoms and subatomic particles, spin takes on an even stranger character. Particles have something called intrinsic spin, a kind of rotation that isn't really rotation in the ordinary sense. An electron's spin is a fundamental property, like its electric charge or mass. It can be spin up or spin down relative to any axis you choose to measure, but it's not literally spinning like a tiny sphere. It's something more abstract, more fundamental, a kind of quantum rotation that has no classical equivalent. And yet, even in this strange quantum realm, time maintains its forward flow, its steady march from past to future. Neutrinos, those ghostly particles that stream through your body by the trillions every second without interacting, have a peculiar relationship with spin. All neutrinos we've ever observed are left-handed, meaning their spin axis points opposite to their direction of motion. It's as if the universe has a subtle preference for left-handedness at the most fundamental level. Some physicists wonder if this handedness preference might be connected to time's arrow, if the universe's choice of left-handed neutrinos is somehow related to its choice of forward-flowing time. We don't know the answer yet, but it's one of many tantalizing hints that spin and time might be more deeply connected than we currently understand. As you drift deeper into relaxation, perhaps beginning to feel that pleasant heaviness that comes before sleep, consider how your own body embodies these cosmic principles. Your DNA spirals in a right-handed double helix, a molecular echo of cosmic rotation. Your proteins fold into complex three-dimensional shapes, many of them with distinct handedness. Your heart beats in a rhythm that marks your personal time, while the Earth's rotation sets your circadian rhythms. You're a collection of cosmic patterns, a temporary arrangement of matter that has learned to spin and flow in harmony with the universe's fundamental rules. The search for understanding why the universe spins in various directions while time flows in, only one has led scientists to some of the most profound questions in physics. Is time fundamental, or does it emerge from something deeper? Are there extra dimensions of time we haven't discovered? Could there be parallel universes where time flows differently? These questions push at the boundaries of human knowledge, taking us to the edge of what we can currently understand about reality. String theory, one attempt to unify all of physics, suggests that there might be extra dimensions of space curled up too small for us to see. In some versions of string theory, there could even be extra dimensions of time, though only one would be extended like the time we experience. These extra time dimensions would be compact, cyclic, perhaps explaining some of the universe's mysterious properties. It's speculative, far from proven, but it hints at how much we still have to learn about the nature of time and space. The cosmic microwave background, that ancient light from the early universe, holds clues about both rotation and time. When scientists analyze its tiny temperature fluctuations, they can see the seeds of all the structure in today's universe, the slight density variations that would grow into galaxies and galaxy clusters. They can also search for any signs of universal rotation, any hint that the cosmos as a whole spins. So far, the universe appears remarkably non-rotating at the larger scales, but the search continues with ever more sensitive instruments. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, found some curious anomalies. There's a slight asymmetry between one hemisphere of the sky and the other, what scientists call the hemispheric asymmetry. There's also something called the cold spot, an unusually large and cold region that doesn't quite fit with our standard models. Some scientists have wondered if these anomalies might be hints of universal rotation or other large-scale properties we don't yet understand. But the evidence remains ambiguous, tantalizing but not conclusive. Future telescopes and observatories will probe these questions with even greater sensitivity. The James Webb Space Telescope is already showing us the universe's earliest galaxies, revealing how rotation and structure emerge from the smooth early cosmos. The upcoming Nancy Grace Roman Space Telescope will survey vast swathes of sky, mapping millions of galaxies and their spins. The square-kilometre array, when complete, will be the world's largest radio telescope, capable of detecting the faint whispers of hydrogen gas from the cosmic dawn. Each of these instruments will add new pieces to our puzzle, helping us understand why the universe spins and time flows as they do. But perhaps the most profound aspect of this cosmic mystery is not the scientific details, but what it means for us as conscious beings embedded in this strange and beautiful universe. We are patterns of matter that have become aware of ourselves, collections of atoms that can contemplate atoms, arrangements of spinning particles that can wonder about spin. We experience time's flow as memory and anticipation, as growth and aging, as the rhythm of days and seasons. We are the universe becoming conscious of itself, able to ask these deep questions about its own nature. Every night when you go to sleep, you participate in a small surrender to time's flow. You let go of consciousness, trusting that time will carry you safely to tomorrow's awakening. Your brain cycles through stages of sleep, each with its own characteristic patterns of neural activity, its own rhythms and frequencies. Dreams unfold in their own strange time, sometimes seeming to last hours in just minutes of real time, sometimes compressing vast adventures into brief moments. Sleep is our nightly journey through time's river, a reminder that we are temporal beings, creatures of duration and change. The rotation of the Earth that brings us day and night is one of the most fundamental rhythms of life. Almost every organism on our planet has evolved circadian rhythms tuned to this 24-hour cycle. Your body temperature rises and falls with the day. Your hormone levels cycle with remarkable precision. Even your cognitive abilities wax and wane with the Earth's rotation. You are, in a very real sense, a biological clock synchronized to a cosmic spinner, your internal time keeping beat with the planet's rotation. As we near the end of this first part of our journey, let's consider one more beautiful connection between spin and time. Black holes, those mysterious objects where gravity becomes so strong that even light cannot escape, are characterized by just three properties: mass, electric charge, and spin. Most black holes are spinning, some at nearly the speed of light. As they spin, they drag spacetime around with them, creating a region called the ergosphere where space itself is pulled into rotation. Inside the ergosphere, nothing can remain stationary. Everything must rotate with the black hole. It's as if the black hole's spin becomes mandatory, inescapable, woven into the very fabric of space. And yet, even at a black hole, time maintains its forward flow. In fact, near a black hole, time's behavior becomes even more extreme. Time dilation grows so strong that someone falling into a black hole would experience only moments, while outside observers would see them frozen at the event horizon for eons. The black hole's spin affects how this plays out, changing the shape of the event horizon, but it never reverses time's direction. Even in the most extreme environments in the universe, where space is twisted and torn, time continues its patient forward flow. This brings us to a profound realization. No matter where we look in the universe, from the smallest subatomic particles to the largest cosmic structures, from the gentle spin of galaxies to the furious rotation of pulsars, from the quantum realm to the cosmic web, we find the same fundamental pattern. Space allows rotation in any direction, but time flows only forward. This asymmetry, this difference between space's democratic treatment of all directions and time's authoritarian insistence on just one, is perhaps the deepest mystery in all of physics. Some scientists believe that understanding this asymmetry will require a new theory of quantum gravity, a framework that successfully merges quantum mechanics with general relativity. Others think we need to reconsider the very nature of time itself, perhaps discovering that it's not fundamental but emergent, arising from something deeper we haven't yet imagined. Still others wonder if the answer lies in the multiverse, if our universe's particular arrow of time is just one possibility among infinite variations. But for tonight, for this moment as you rest in the darkness, perhaps the mystery itself is enough. Perhaps there's something beautiful in not knowing, in recognizing that we live in a universe still full of profound questions. The fact that galaxies spin while time flows forward, that rotation can go any direction while time knows only one. This is not a problem to be solved, but a wonder to be appreciated. It's part of the cosmic poetry that makes our universe what it is. Consider how different things would be if time could flow backward as easily as forward. Memory would be meaningless, cause and effect would lose their power, stories could not be told. Life itself depends on time's arrow, on the ability to grow and learn and change in a consistent direction. The universe's choice to make time flow only forward is what allows us to exist, to experience, to wonder about these very questions. In a universe where time could reverse, we couldn't be here contemplating the mystery. Similarly, imagine a universe where nothing could rotate, where spin was forbidden by the laws of physics. There would be no galaxies, no solar systems, no planets. The universe would be a very different place, probably incapable of supporting the kind of complex structures that lead to life. Rotation is essential for creating the diverse environments where chemistry can become biology, where matter can organize itself into thinking, feeling beings like us. So perhaps the universe spins in many directions and time flows in one, because this is the combination that allows for the richest possible existence, the most interesting stories, the greatest diversity of experiences. Perhaps we live in a universe fine-tuned not just for life, but for wonder, for beauty, for the kind of cosmic poetry that emerges when rotation and time's arrow dance together through the darkness. As you continue to drift towards sleep, feeling perhaps that pleasant dissolution of boundaries that comes when consciousness begins to fade, remember that you are part of this cosmic dance, The atoms in your body are spinning, the Earth beneath you is rotating, the galaxy around you is turning, and through it all, time is carrying you gently forward into tomorrow. You're not separate from these cosmic processes, but an intimate part of them, a temporary pattern in the universe's vast flow, a moment of awareness in time's river. The question of why the universe spins in one direction but time only flows in another is really a question about existence itself, about why reality takes the particular form it does. And while we may never fully answer this question, the search for understanding is itself a beautiful part of being human, part of what makes us more than just collections of spinning atoms. We are the universe's way of contemplating itself, of wondering about its own nature, of finding beauty in its own mysteries. As we continue our journey deeper into this cosmic mystery, let's turn our attention to something remarkable that scientists have been quietly investigating for decades. Does the universe itself, the entire cosmos taken as a whole, rotate? It's a question that might seem almost too vast to contemplate, yet it's one that astronomers have been carefully probing with increasingly sophisticated instruments and observations. Imagine, if you will, that everything we can see, every galaxy, every cluster, every filament of the cosmic web, all of it might be part of one vast, slowly turning system, like a cosmic carousel so large that we can barely perceive its motion from our tiny vantage point on Earth. The search for universal rotation began in earnest when cosmologists started mapping the cosmic microwave background radiation with unprecedented precision. This ancient light, released when the universe was only 380,000 years old, carries within it subtle patterns and fluctuations that tell us about the universe's earliest moments and its larger scale properties. If the universe as a whole were rotating, even incredibly slowly, it would leave distinctive signatures in this primordial light, patterns that would break the otherwise remarkable symmetry we observe. Scientists have searched for these telltale signs, with satellites like COBE, WMAP, and most recently Planck, each one more sensitive than the last, each one peering deeper into the cosmic background for any hint of a universal spin. What they've found is both disappointing and profound. The universe, as far as we can tell, does not rotate as a whole. The cosmic microwave background shows remarkable isotropy, meaning it looks essentially the same in all directions. There's no preferred axis of rotation, no cosmic north, pole around which everything spins. The stage upon which all cosmic motion takes place appears to be perfectly still, or at least so close to still that we cannot detect any rotation with our current instruments. This non-rotation is actually quite mysterious in its own right, because it means the universe began in an extraordinarily special state, one with essentially zero net angular momentum, despite all the local rotations we see everywhere we look. Think about what this means for a moment. In a universe filled with spinning galaxies, rotating stars, orbiting planets, and whirling particles, the sum total of all these rotations appears to cancel out to zero, or very close to zero. It's as if the universe is a vast ballet where countless dancers spin in various directions, but the stage itself remains motionless, providing a fixed reference frame against which all these individual rotations can be measured. This is deeply connected to something physicists call the cosmological principle, the idea that the universe is homogeneous and isotropic on the larger scales, looking the same in all directions and from all vantage points. But the story doesn't end there. While the universe as a whole may not rotate, scientists have discovered something even more intriguing. When they look at the spins of galaxies across vast regions of space, they sometimes find subtle correlations, faint patterns that suggest the universe might have a kind of handedness or chirality on large scales. Some surveys have found slight excesses of galaxies spinning one way versus the other in certain regions of the sky. These findings are controversial and not yet conclusive, but they hint at the possibility that while the universe doesn't rotate globally, it might have local preferences for rotation that vary from place to place. The Sloan Digital Sky Survey, which has mapped millions of galaxies across a significant fraction of the observable universe, has been crucial in these investigations. When astronomers analyze the spin directions of spiral galaxies in this vast dataset, they look for any statistical preferences, any departures from random distribution. Some studies have reported finding such preferences, with galaxies in one part of the sky showing a slight tendency to spin clockwise while those in another part prefer counterclockwise. but other studies have failed to confirm these findings, and the debate continues in the scientific community. What could cause such patterns if they're real? One possibility is that they're fossils from the very early universe, remnants of quantum fluctuations during cosmic inflation that got stretched to cosmic scales. Another possibility is that they're caused by the large-scale structure of the universe itself, with galaxies acquiring preferential spins based on their location within the cosmic web. Or perhaps they're just statistical flukes, patterns our pattern-seeking brains perceive in what is actually random data. The jury is still out, and more observations are needed to settle the question. Meanwhile, the search for universal rotation continues with ever more creative methods. Some scientists have looked at the polarization of a light from distant quasars, searching for any systematic rotation of polarization angles that might indicate universal rotation. Others have studied the cosmic microwave background's polarization patterns, looking for the particular signatures that rotation would create. Still others have examined the distribution of galaxy clusters, searching for any asymmetries that might reveal a cosmic spin. So far, all these searches have come up empty or ambiguous, but the null result itself tells us something important about the universe we inhabit. The upper limits on universal rotation that these observations provide are extraordinarily stringent. If the universe is rotating, it must be doing so incredibly slowly, completing less than one rotation over its entire 13.8 billion year history. To put this in perspective, imagine a carousel that takes longer than the age of the universe to complete a single turn. You wouldn't be able to perceive its motion even if you watched for billions of years. This is the kind of rotation we're talking about, so slow it's essentially indistinguishable from no rotation at all. But let's consider for a moment what it would mean if the universe did rotate, even infinitesimally slowly. It would imply that the universe has a preferred direction, an axis around which everything turns. This would break the symmetry we observe and would have profound implications for our understanding of cosmology. It might mean that physics itself could be slightly different in different directions, that there could be a preferred frame of reference after all, contradicting one of the fundamental assumptions of relativity. It would be a discovery that would shake the foundations of modern physics. The absence of detectable universal rotation also tells us something important about the Big Bang itself. In the standard model of cosmology, the universe began in a state of extremely high temperature and density, with matter and energy distributed almost perfectly uniformly. Any initial rotation would have been amplified as the universe expanded, potentially leading to observable effects today. The fact that we see no such effects suggests that the universe began with essentially zero angular momentum, a condition that seems almost impossibly special given all the ways the universe could have started. This connects to one of the deep mysteries in cosmology known as the flatness problem. Observations show that the universe is remarkably flat, meaning that parallel lines remain parallel even over cosmic distances, that the angles of triangles add up to 180 degrees even when the triangles span billions of light years. This flatness, combined with the absence of rotation, suggests that the universe began in an extraordinarily special state, fine-tuned to an almost unbelievable degree. The theory of cosmic inflation was developed partly to explain this fine-tuning, proposing that a period of exponential expansion in the universe's first fraction of a second could have flattened any initial curvature and diluted any initial rotation to undetectable levels. Now, while the universe as a whole may not rotate, individual structures within it certainly do, and in fascinating ways. Let's explore one of the most extreme examples of cosmic rotation: black holes. These objects, where gravity becomes so strong that it tears holes in the fabric of spacetime itself, can spin at tremendous rates. When a massive star collapses to form a black hole, it conserves its angular momentum, causing the resulting black hole to spin faster and faster as it shrinks, like a figure skater pulling in their arms during a spin. Some black holes spin so fast that they approach the theoretical maximum rate allowed by Einstein's general relativity, where the event horizon at the equator would be moving at nearly the speed of light. These rapidly rotating black holes, called Kerr black holes after the mathematician who first solved Einstein's equations for them, have properties that seem almost magical. They drag spacetime around with them in a phenomenon called frame dragging, or the lens-thirring effect, creating a region called the ergosphere where nothing can remain stationary relative to distant stars. The spin of a black hole profoundly affects the spacetime around it. While a non-rotating black hole has a perfectly spherical event horizon, a rotating black hole's event horizon is flattened at the poles and bulging at the equator, like a squashed sphere. The faster it spins, the more pronounced this distortion becomes. The ergosphere, that region where space itself is dragged into rotation, extends beyond the event horizon, creating a zone where strange physics prevails. Objects entering the ergosphere must rotate with the black hole, regardless of their own preferences. It's as if the black hole's rotation becomes mandatory, written into the very structure of space and time. Scientists can actually measure the spins of black holes, both through observations of matter falling into them and through gravitational waves. When hot gas spirals into a black hole, forming what's called an accretion disk, the inner edge of this disk depends on the black hole's spin. The faster the black hole rotates, the closer matter can orbit before falling in, and the hotter and brighter the inner disk becomes. By analysing the X-ray emissions from these accretion disks, astronomers can determine how fast the black hole is spinning. Many of the black holes we've measured this way are spinning at significant fractions of the maximum possible rate. Gravitational waves provide another window into black hole rotation. When two black holes merge, they emit gravitational waves that carry information about their masses and spins. The LIGO and Virgo detectors have now observed dozens of these mergers, revealing a population of black holes with a wide range of spin rates. Some are barely spinning at all, while others are rotating rapidly. The final black hole produced by a merger typically spins faster than either of its progenitors, as the orbital angular momentum of the system gets converted into spin. These observations are giving us unprecedented insights into how black holes form and evolve. The Event Horizon Telescope, which produced the first images of black holes, has shown us the shadows of rotating black holes directly. The supermassive black hole at the centre of the galaxy M87, which weighs as much as 6.5 billion suns, is spinning, though not at the maximum rate. The shape and brightness distribution of its shadow reveal this spin, with one side of the accretion disk appearing brighter due to relativistic beaming, an effect where light from matter moving toward us is boosted, while light from matter moving away is dimmed. It's as if we can see the black hole's rotation frozen in a snapshot of twisted light. But here's where things get even more interesting. Despite all this spinning, despite the way rotating black holes twist space and time into knots, time still flows in only one direction near a black hole. In fact, the presence of a black hole makes time's one-way nature even more extreme. Inside the event horizon, space and time switch roles in a sense. The radial direction becomes time-like, meaning that falling toward the singularity becomes as inevitable as moving forward in time. No amount of rotation, no amount of angular momentum can change this fundamental fact. Time's arrow remains supreme, even in the most extremely twisted space-time we know of. This brings us to a fascinating speculation. Some physicists have wondered whether rotating black holes might offer a way to travel backward in time. The mathematics of general relativity does allow for something called closed time-like curves near rotating black holes, pass through space-time that loop back to their own past. But these solutions likely don't represent physical reality. They require conditions that probably can't exist in our universe, like matter with negative energy density or naked singularities without event horizons. Even in the extreme environment of a rotating black hole, time travel to the past remains forbidden, another testament to time's stubborn insistence on flowing in just one direction. Let's shift our attention now to something more subtle, but equally profound: the role of quantum mechanics in cosmic rotation. At the quantum level, particles have an intrinsic property called spin that isn't quite like classical rotation, but shares some of its characteristics. Every electron, every quark, every photon has spin, and this quantum spin is absolutely fundamental to how our universe works. Without it, atoms couldn't exist in their current form, chemistry would be impossible, and we wouldn't be here to wonder about it. Quantum spin comes in discrete units, unlike classical rotation, which can take any value. Electrons have spin 1-2, meaning they must rotate through 720 degrees to return to their original state, a property that has no classical analogue. Photons have spin 1, while the hypothetical graviton would have spin 2. These different spin values determine how particles behave, what kinds of forces they can carry, and how they interact with each other. The entire structure of matter and forces in our universe is intimately connected to these quantum spins. One of the most remarkable discoveries in particle physics is that the universe seems to have a preference for left-handedness at the quantum level. This shows up most clearly in the weak nuclear force, one of the 4 fundamental forces of nature. When neutrons decay into protons, electrons, and antineutrinos, a process governed by the weak force, the electrons are preferentially emitted with their spins opposite to their direction of motion, what physicists call left-handed. The neutrinos produced in these decays are always left-handed, never right-handed. It's as if the universe has chosen a preferred handedness at its most fundamental level. This violation of parity, or mirror symmetry, was one of the most shocking discoveries in 20th century physics. Until 1956, physicists assumed that the laws of physics would be the same in a mirror-reversed universe. But experiments by Chien-Shiung Wu and others showed definitively that this isn't true. The weak force can tell left from right, breaking the mirror symmetry we might have expected. This parity violation is built into the standard model of particle physics and may be connected to why our universe contains matter rather than antimatter. The connection between this quantum handedness and the arrow of time is subtle but profound. In 1964, physicists discovered that certain particles called kaons violate what's called CP symmetry, the combination of charge conjugation and parity. This means that the laws of physics aren't quite the same if you reverse all charges and look in a mirror. According to something called the CPT theorem, one of the most fundamental results in quantum field theory, if CP is violated, then time reversal symmetry must also be violated to maintain the overall CPT symmetry. In other words, the universe's preference for left-handedness is intimately connected to its preference for forward-flowing time. This CP violation might be responsible for our very existence. In the early universe, matter and antimatter should have been created in equal amounts, and they should have annihilated each other completely, leaving nothing but radiation. But somehow a tiny excess of matter survived, about 1 extra matter particle for every billion matter-antimatter pairs. This tiny asymmetry is what all the galaxies, stars, planets, and people are made from. Many physicists believe that CP violation is the key to understanding this antimatter asymmetry, though the CP violation we've observed so far isn't quite enough to explain the excess of matter we see. The search for additional sources of CP violation is one of the major goals of particle physics. Experiments at the Large Hadron Collider and other facilities are looking for new particles and interactions that might violate CP symmetry more strongly than what we've seen so far. Some theories predict that dark matter, the mysterious substance that makes up most of the matter in the universe, might violate CP symmetry in ways we haven't yet detected. If so, understanding dark matter might also help us understand why time flows forward and why the universe has the particular handedness we observe. Let's consider now how cosmic structure itself learns to rotate. Galaxies don't form spinning. They acquire their rotation over time through a process that's both simple in principle and breathtakingly complex in detail. In the early universe, matter was distributed almost uniformly, with tiny density fluctuations of only about 1 part in 100,000. These fluctuations, which we can see imprinted in the cosmic microwave background, were the seeds from which all structure would grow. As gravity pulled matter together, these small fluctuations grew larger. Regions that were slightly denser than average attracted more matter, becoming denser still. But here's the crucial point. These growing structures were not perfectly spherical. They had slight asymmetries, slight departures from perfect uniformity. And in a universe filled with other growing structures, these asymmetries experienced different gravitational forces from different directions. These differential forces, called tidal torques, caused the structures to begin rotating. Computer simulations of structure formation, like the Millennium simulation and the Illustris project, have shown this process in exquisite detail. Starting from the tiny fluctuations observed in the cosmic microwave background, these simulations follow the gravitational collapse and merger of dark matter halos, the formation of galaxies within them, and the development of the cosmic web. They show how galaxies acquire their spin through tidal interactions during their formation, typically reaching peak rotation rates when they're about half their current age. The amount of rotation a galaxy acquires depends on its particular history, its environment, and the details of how it formed. Galaxies that formed through relatively quiet accretion tend to be rotating disks, like our own Milky Way. Those that experience major mergers often become elliptical galaxies with less organized rotation. The most massive galaxies, which sit at the centers of galaxy clusters, often rotate very slowly or not at all, having been built up through many mergers that randomize the motions of their stars. But here's something beautiful. Despite all this complexity, there are simple scaling relations that connect a galaxy's rotation to its other properties. The Tully-Fisher relation, for example, links a spiral galaxy's rotation speed to its total luminosity. The faster a galaxy spins, the brighter it tends to be. This relation is so tight that astronomers use it to measure distances to galaxies, inferring their true brightness from their rotation speed and comparing it to their apparent brightness to determine how far away they are. Recent observations with the Atacama Large Millimeter Array have shown us galaxies in the early universe, when the cosmos was only 1 billion years old, that were already rotating in organized disks. This was surprising because many astronomers expected early galaxies to be more chaotic, taking billions of years to settle into regular rotation. But these observations show that cosmic rotation can organize itself remarkably quickly, that the universe learned to spin earlier than we thought. The James Webb Space Telescope is now pushing these observations even further back in time, showing us galaxies when the universe was only a few 100 million years old. Some of these earliest galaxies already show signs of rotation, though they are often more irregular and asymmetric than nearby galaxies. It's as if we're watching the universe learning to dance, starting with awkward, stumbling steps, and gradually developing into the graceful spirals we see today. The cosmic web itself, that vast network of filaments and voids that defines the large-scale structure of the universe, plays a crucial role in how galaxies acquire their spin. Galaxies form along these filaments, where matter flows like cosmic rivers toward the nodes where galaxy clusters grow. The direction of a galaxy's spin is often correlated with its orientation relative to the nearest filament, as if the filament acts like a cosmic spindle, setting galaxies turning as they form. Recent surveys have found that these spin filament alignments extend over millions of light years, connecting the rotation of individual galaxies to the largest structures in the universe. It's a remarkable example of how local and global properties are connected in cosmology, how the spin of a single galaxy can be influenced by structures vastly larger than itself. The universe is not just a collection of isolated spinning objects, but an interconnected system where rotation on one scale influences rotation on another. Dark matter, which makes up about 85% of all matter in the universe, plays a crucial but invisible role in all of this. Galaxies form within halos of dark matter, vast spherical regions where dark matter's gravity has collected both dark and ordinary matter. These dark matter halos begin rotating through the same tidal Torquing process that affects ordinary matter, and they pass this rotation on to the galaxies that form within them. In a very real sense, it's dark matter that teaches ordinary matter how to spin, even though we've never directly detected a dark matter particle. The interplay between dark matter and ordinary matter in rotating systems is complex and not fully understood. In spiral galaxies, the rotation curves, graphs of how fast stars orbit at different distances from the center, provide some of our strongest evidence for dark matter. Stars in the outer parts of galaxies orbit much faster than they should based on the visible matter alone, implying the presence of vast amounts of invisible mass. This dark matter doesn't just add mass, it fundamentally shapes how galaxies rotate, maintaining their flat rotation curves over vast distances. But there's a puzzle here known as the cuspy halo problem. Simulations of dark matter predict that it should be densely concentrated at the centers of galaxies, but observations suggest that dark matter is more evenly distributed. Some astronomers think that the rotation of ordinary matter, particularly the spiral density waves in galactic disks, might redistribute dark matter, smoothing out the central concentration. If so, it would be a beautiful example of how rotation allows ordinary and dark matter to influence each other, despite dark matter's ghostly reluctance to interact through any force but gravity. As we contemplate these cosmic rotations, from the quantum spin of particles to the majestic turning of galaxies, it's worth pausing to consider what this means for us, for our place in this vast spinning cosmos. We live on a small planet orbiting an ordinary star in the outer regions of one galaxy, among hundreds of billions, and yet we're intimately connected to all these scales of rotation. The iron in our blood was forged in rotating stars. The carbon in our DNA was dispersed by rotating supernovae. The stability of our solar system depends on the precise balance of rotational and gravitational forces. Our own Milky Way galaxy is rotating right now, carrying our solar system around its center at about 230 kilometers per second. At this speed, it takes our Sun about 225 million years to complete one orbit around the galaxy, a period sometimes called a cosmic year. Since the Sun formed 4.5 billion years ago, we've completed only about 20 cosmic years. Dinosaurs lived just one cosmic year ago. The entire history of human civilization, from the first agriculture to the present day, spans less than 0.5 cosmic years. We are truly ephemeral beings living on a slowly turning cosmic carousel, but even as we're carried around the galaxy, time continues its relentless forward march. Each rotation of the Earth brings a new day, each orbit around the Sun brings a new year, each galactic rotation brings a cosmic year, but none of these cycles ever truly repeat. Time ensures that each day is unique, that we can never return to yesterday, that the universe is constantly writing new history rather than repeating old patterns. The combination of cyclic rotation and linear time creates a spiral structure to existence, where patterns repeat but never exactly, where the familiar and the novel are constantly intertwined. This spiral nature of existence shows up everywhere we look. The DNA in our cells is a double helix, a spiral structure that combines rotation with linear extension. Snail shells grow in logarithmic spirals, combining rotation with expansion. Weather systems are spirals, hurricanes and cyclones that combine rotation with forward motion. Even our galaxy has spiral arms, density waves that rotate at a different rate than the stars, creating patterns that persist even as individual stars move in and out of them. Spirals are perhaps nature's favorite shape, the natural result of combining rotation with time's forward flow. As you lie there, perhaps feeling the gentle pull of sleep beginning to take hold, consider how your own consciousness participates in these cosmic patterns. Your thoughts don't simply cycle, they spiral, returning to familiar themes, but always with new perspectives, new connections. Your memories aren't static, they evolve each time you recall them, influenced by everything that's happened since. Your dreams tonight will combine familiar elements in new ways, your sleeping brain creating novel patterns from the rotating kaleidoscope of your experiences. The question of why the universe allows rotation in any direction but restricts time to just one might not have a single, simple answer. It might be that this asymmetry is fundamental, built into the deepest laws of nature in ways we don't yet understand. Or it might emerge from something even deeper, some underlying principle or symmetry that we haven't yet discovered. The search for understanding continues, with each generation of scientists adding new pieces to the puzzle, approaching the mystery from new angles. What we do know is that this combination, multi-directional rotation plus unidirectional time, creates a universe of extraordinary richness and beauty. It allows for both stability and change, pattern and novelty, predictability and surprise. It creates the conditions for complexity to emerge and evolve, for simple laws to give rise to intricate structures, for matter to organize itself into living, thinking beings capable of contemplating their own existence. The ancient Greeks imagined the cosmos as crystalline spheres rotating around the Earth, carrying the planets and stars in their eternal cycles. We now know the universe is far stranger and more wonderful than they imagined, filled with rotating objects at every scale but without any universal rotation, governed by time that flows always forward but at different rates in different places. Our modern cosmology would seem like magic to them, and perhaps it should seem like magic to us too. The fact that we can understand any of this, that we can measure the spin of distant galaxies and the flow of time near black holes, is itself a kind of cosmic miracle. As we prepare to explore even deeper mysteries in the final part of our journey, let's appreciate where we are right now. We live in a universe where rotation creates structure and beauty at every scale, from the quantum to the cosmic. We live in a universe where time provides the canvas on which the story of existence is written, always forward, never backward. We live in a universe that somehow allows matter to organize itself into patterns complex enough to become aware of themselves, to wonder about their own nature, to search for meaning in the cosmic dance. The relationship between cosmic patterns and earthly experience becomes most intimate when we consider how rotation and time shape our daily lives, our biological rhythms, and our very consciousness. As you rest there in the darkness, your body is performing an ancient dance with time, one that connects you to the cosmos in ways both profound and practical. Your heartbeat, that most personal of rhythms, marks out your own internal time, about 100,000 beats per day, roughly 2.5 billion beats in a lifetime. Each beat sends blood spiraling through your arteries in helical flows, rotation and forward motion combined, echoing the same spiral patterns we see in galaxies and hurricanes. Your circadian rhythms, those internal clocks that govern when you feel alert or sleepy, when your body temperature rises and falls, when your hormones surge and ebb, are synchronized to Earth's rotation with remarkable precision. Deep in your brain, in a tiny region called the suprachiasmatic nucleus, about 20,000 neurons fire in coordinated waves, keeping time with an accuracy that would have astounded clockmakers of previous centuries. These neurons don't just respond to light and darkness, they maintain their rhythm even in constant conditions, a biological clock that runs on its own but adjusts itself to Earth's rotation through signals from your eyes. The discovery of these molecular clocks revolutionized our understanding of biology. In every cell of your body, specific proteins accumulate and degrade in cycles that take almost exactly 24 hours. The genes that code for these proteins, with names like period and clock and cryptochrome, are found in organisms from bacteria to humans, an ancient timekeeping system that predates the emergence of complex life. These cellular clocks don't just tell time, they coordinate virtually every aspect of your physiology, from metabolism to immune function to DNA repair. When you fly across time zones and experience jet lag, you're feeling the temporary misalignment of these myriad cellular clocks as they slowly resynchronize to the new pattern of day and night. But humans haven't been content to simply live by nature's rhythms. We've built our own systems for measuring and coordinating time, technologies that have become so precise they reveal the malleable nature of time itself. Atomic clocks, which measure time by counting the oscillations of cesium atoms, can keep time to better than 1 second in 100 million years. These clocks are so sensitive that they can detect the effects of Einstein's relativity in everyday situations. A clock placed on a table runs slightly faster than one on the floor because it's farther from Earth's centre of gravity. A clock in a moving car runs slightly slower than one at rest. These effects are tiny, measured in nanoseconds, but they're real and measurable. The global positioning system satellites orbiting overhead must account for both these effects to maintain the accuracy we've come to depend on. Without corrections for relativity, GPS positions would drift by about 10 kilometers per day. Think about that for a moment. The phone in your pocket, or the GPS in your car, works only because we understand how gravity and motion affect the flow of time. Every time you use GPS to navigate, you're conducting a practical experiment in Einstein's relativity, confirming that time is not the absolute uniform quantity that Newton imagined, but something that bends and stretches with gravity and motion. This technological precision has revealed something remarkable about Earth's rotation itself. Our planet's spin is not perfectly constant. The length of a day varies by milliseconds due to a variety of factors. The gravitational pull of the Moon and Sun causes tidal bulges in Earth's oceans and solid body, and the friction of these tides gradually slows our planet's rotation. Days are getting longer by about 1.8 milliseconds per century. When the dinosaurs roamed Earth, a day was perhaps 30 minutes shorter than today. In the distant future, billions of years from now, Earth's rotation will have slowed so much that one side will permanently face the Moon, just as the Moon now keeps one face toward Earth. But there are shorter-term variations too. Large earthquakes can shift Earth's mass distribution, changing the length of a day by microseconds. The seasonal movement of water and air masses causes predictable variations in rotation rate. Even the growth of leaves in spring and their fall in autumn creates a measurable effect on Earth's spin. Climate change is affecting Earth's rotation too, as melting ice sheets redistribute water from the poles toward the equator, slightly slowing our planet's spin like a figure skater extending their arms. To keep our clocks synchronized with Earth's rotation, we occasionally add leap seconds, moments when official time pauses for 1 second to let Earth catch up. Since 1972, we've added 27 leap seconds, each one a tiny acknowledgement that human timekeeping and cosmic rotation are separate systems that must be actively kept in alignment. It's a humbling reminder that for all our technological precision, we still set our clocks by the turning of our planet, still measure our days by Earth's patient, Spin. The way we experience time psychologically is itself a fascinating interplay of rotation and linear flow. Your brain doesn't simply track time, it constructs it from a combination of internal rhythms and external cues. Different brain regions operate on different timescales. The brainstem generates rhythms of milliseconds for coordinating movement. The hippocampus creates theta waves of about 8 cycles per second during navigation and memory formation. Slower rhythms coordinate sleep stages, cycling through periods of deep sleep and REM sleep about every 90 minutes. Memory gives us our personal arrow of time, our sense of before and after, cause and effect. But memory isn't a simple recording. Each time you recall an event, you reconstruct it, potentially changing it in the process. Your memories of yesterday are different from your memories of last year, not just in clarity but in meaning, coloured by everything that's happened since. In this way, your personal experience of time is constantly being revised, even as it flows irreversibly forward. The past isn't fixed in memory, but continuously reinterpreted through the lens of the ever-changing present. Dreams reveal another aspect of how consciousness relates to time. In dreams, time can behave strangely. Events can happen out of sequence, past and future can merge, and long adventures can unfold in the few minutes of a REM cycle. Some researchers believe dreams are the brain's way of consolidating memories, transferring information from temporary storage to long-term memory, creating associations and patterns that help us navigate the waking world. In this view, the strange time of dreams is the brain organizing its temporal experience, filing away the day's events while simultaneously preparing for tomorrow's challenges. The development of human consciousness itself can be seen as evolution discovering how to use time more effectively. Simple organisms respond only to immediate stimuli, living in an eternal present. More complex animals can learn from past experiences, adjusting their behavior based on memory. But humans have developed something even more sophisticated: the ability to mentally travel through time, to vividly imagine future scenarios and plan accordingly, to tell stories that preserve experiences across generations, to build cultures that accumulate knowledge over millennia. This mental time travel, what psychologists call episodic future thinking, might be humanity's defining cognitive ability. When you imagine tomorrow's meeting or next year's vacation, you're doing something that few, if any, other animals can do with such richness and flexibility. You're using the same brain networks that recall past experiences to construct detailed simulations of possible futures. This ability to project ourselves forward in time while learning from the past is what allows us to make complex plans, to delay gratification for future rewards, to work toward goals that may take years or decades to achieve. Language itself is a technology for transcending time's limitations. Through words, we can share experiences across time, transmitting thoughts from one mind to another, preserving ideas beyond the lifespan of their creators. The words you're hearing now were composed in my past but exist in your present, creating a bridge across time through the medium of language. Writing extended this power even further, allowing messages to survive for millennia. The ancient Sumerians who invented writing couldn't have imagined that their clay tablets would be read 5,000 years later, but their thoughts have travelled through time to reach us, defeating time's erasure through the persistence of symbols carved in clay. Our modern information age has accelerated this time-transcending quality of human culture to an extraordinary degree. The internet contains a vast archive of human thought and experience, petabytes of data preserving billions of moments, thoughts, images, and ideas. Every photo you take, every message you send, every thought you share online becomes part of this collective memory, a vast externalization of human consciousness that exists outside of time's normal flow. Future generations will have access to a record of daily life in our era that's unprecedented in its detail and scope. But even as we build these elaborate systems for preserving and sharing information across time, we remain biological beings subject to time's arrow. We age in one direction, from young to old, our bodies gradually accumulating the wear and tear of existence. The second law of thermodynamics applies to us just as surely as it applies to stars and galaxies. Our highly ordered biological systems require constant energy input to maintain themselves against entropy's pull. When that energy flow stops, when our hearts cease their rhythmic beating, we return to equilibrium with our environment, Are atoms dispersing to become part of other patterns, other stories? Yet there's something beautiful in this temporality, this finite span we're given. The fact that our time is limited is what gives it value, what makes each moment precious. If we lived forever, would a sunset be as beautiful? Would a child's laughter be as joyful? Would love be as intense? The arrow of time, which seems at first like a limitation, is actually what creates meaning, what allows for growth and change and story. Without time's irreversible flow, there could be no narrative, no development, no journey from beginning through middle to end. Consider how different human cultures have conceptualized time, each offering a unique perspective on its nature. Western linear time sees history as progress, moving from past through present toward future in a straight line. Hindu and Buddhist cyclic time imagines vast cosmic cycles, kalpas and yugas, wheels within wheels of creation and destruction. Indigenous Australian Dreamtime sees past, present, and future as simultaneously accessible through ritual and story. The Aymara people of the Andes think of the past as in front of them, because it can be seen or known, while the future is behind them, unseen and unknown. Modern physics has given us yet another perspective, where time is not universal but relative, where past, present, and future are human constructs imposed on a four-dimensional space-time continuum. In relativity, there's no universal now that extends throughout the universe. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different velocity. The universe doesn't have a single timeline, but rather a complex web of world lines, paths through space-time that weave together in patterns determined by gravity and motion. Some physicists have proposed that time might be emergent rather than fundamental, arising from something deeper. In loop quantum gravity, one approach to unifying quantum mechanics with general relativity, time emerges from the quantum interactions of space itself. In this view, at the smallest scales, smaller than the Planck length of 10⁻35 meters, space and time lose their meaning, becoming a quantum foam of probabilistic fluctuations. The smooth space-time we experience emerges from these fluctuations the way temperature emerges from the motion of atoms, a statistical property of large collections rather than a fundamental feature of reality. Other theories suggest even more radical possibilities. The holographic principle proposes that all the information in a volume of space can be encoded on its boundary, like a hologram that creates a three-dimensional image from a two-dimensional surface. If this is true, our three-dimensional universe might be a projection from information encoded on a distant two-dimensional surface, and time might be part of this projection, an artifact of how information is processed rather than a fundamental dimension. But for all these exotic possibilities, for all the strange implications of modern physics, our everyday experience of time remains stubbornly classical. We wake each morning to a new day, never to yesterday. We plan for tomorrow, not last week. We remember the past, not the future. This psychological arrow of time, our subjective experience of time's flow, remains one of the deepest puzzles in science. How does the subjective feeling of now arise from the objective physics of space-time? Why do we experience time as flowing when physics suggests it might be more like a static four-dimensional block? Some philosophers and physicists argue that the flow of time is an illusion, that all moments exist eternally in the block universe of space-time, and our sense of flow comes from the way consciousness navigates through this static structure. Others maintain that time's flow is fundamental, that consciousness reveals something about time that physics hasn't yet captured. This debate touches on some of the deepest questions in philosophy: the nature of consciousness, the relationship between subjective experience and objective reality, the meaning of existence itself. As we near the end of our cosmic journey, let's return to the central mystery we've been exploring. Why does the universe allow rotation in any direction but restrict time to just one? Perhaps the answer lies not in physics but in philosophy, not in equations but in understanding. Perhaps the universe has this particular structure because it's the only structure that allows for observers like us to exist and wonder about it. This is the anthropic principle, the idea that the universe's properties are constrained by the requirement that they allow for the existence of observers. If time could flow backward as easily as forward, if effects could precede causes, if entropy could spontaneously decrease, could complex structures like living beings exist? Could evolution occur? could consciousness arise. The irreversibility of time might be not just a feature of our universe, but a requirement for any universe containing observers capable of contemplating time. We observe time flowing in one direction because that's the only kind of universe where observers can exist. Similarly, the freedom of rotation in three-dimensional space might be necessary for the kind of complexity we see in the universe. If rotation were restricted to a single plane or direction, would galaxies form their beautiful spiral structures? Would solar systems achieve stable orbits? Would the complex chemistry of life be possible? The combination of rotational freedom and temporal constraint might be precisely what's needed to create a universe rich with structure and story, pattern and narrative, beauty and meaning. But perhaps seeking an ultimate answer misses the point. Perhaps the question itself is more valuable than any answer could be. The fact that we can ask why the universe spins in one direction, but time flows in another, the fact that we can perceive this asymmetry and wonder about it, this might be the real miracle. We are the universe becoming conscious of itself, able to observe its own patterns and puzzles, to appreciate its own beauty and mystery. Think about what's happening right now in this very moment. Atoms forged in ancient stars have organized themselves into neurons in your brain. These neurons are firing in patterns that somehow generate consciousness, creating an inner experience of sound and meaning from the vibrations of air molecules. You're comprehending ideas about space and time, rotation and flow, cosmos and consciousness. You're participating in a conversation that spans billions of years of cosmic evolution and thousands of years of human thought. This is extraordinary when you really think about it. This capacity for matter to contemplate itself, for the universe to wonder about its own nature. As you lie there, perhaps on the edge of sleep now, feeling the gentle pull of dreams beginning to tug at your consciousness, consider how perfectly positioned you are in the cosmic story. You exist at a time when the universe is neither too young nor too old, when stars still shine and planets still orbit, when the cosmic web is rich with structure and beauty. You exist on a planet perfectly positioned around a stable star, with just the right rotation rate to create days and nights of reasonable length, with just the right orbit to create seasons that mark the passage of years. You exist as a conscious being capable of perceiving both the cycles of rotation and the arrow of time, able to remember the past and imagine the future, to see patterns in the stars and find meaning in their motions. You are a temporary arrangement of matter and energy that has somehow become aware of its own temporary nature, finding beauty and meaning not despite this temporariness but because of it. Every moment of your existence is a victory over entropy, a brief flowering of consciousness in the vast garden of spacetime. The atoms in your body have been on an incredible journey to reach you. They've been part of interstellar clouds and stellar nurseries. They've been forged in stellar cores and dispersed in supernova explosions. They've drifted through space and accumulated into planets. They've been part of rocks and oceans and atmosphere. They've been incorporated into countless living beings before becoming part of you. And they'll continue their journey after you, becoming part of other patterns, other stories, other moments of consciousness contemplating the cosmos. This is the deep connection between the cosmic and the personal, between universal principles and individual experience. The same laws that govern the spin of galaxies govern the electrons in your brain. The same arrow of time that drives the universe toward its distant future carries you through your life from birth to death. The same patterns that create spiral galaxies create the spiral shells of snails and the spiral waves of your inner ear that allow you to hear these words. You're not separate from the cosmic dance, but an integral part of it, a moment where the universe achieves self-awareness. And now, as our journey together draws to a close, as these thoughts and words spiral gently toward their conclusion, we return to where we began, but with deeper understanding. The universe spins in many directions because space offers that freedom, that democracy of motion that allows for the rich diversity of structures we observe. Time flows in one direction because that arrow, that asymmetry, is what allows for story, for growth, for the kind of organized complexity that leads to life and consciousness. These two facts, rotation's freedom and time's arrow, are not contradictions but complementary aspects of a universe exquisitely structured for the emergence of complexity and beauty. They are the warp and weft of the cosmic fabric, the interweaving patterns that create the tapestry of existence. Without rotation, the universe would lack structure and diversity. Without time's arrow, it would lack story and meaning. Together, they create the conditions for the most remarkable phenomenon we know, the emergence of matter that can contemplate matter, of patterns that can perceive patterns, of the universe waking up to its own existence. Perhaps tomorrow, when you wake to Earth's ancient rotation bringing you another dawn, you'll remember something of this journey we've taken together. Perhaps you'll feel, even if just for a moment, your connection to the cosmic dance, your participation in the vast choreography of spinning matter and flowing time. Perhaps you'll appreciate the extraordinary privilege of being conscious in this universe, of being able to witness and wonder at its patterns and mysteries. The questions we've explored tonight don't have final answers, and perhaps they never will. Why does the universe exist at all? Why these particular laws and not others? Why is there something rather than nothing? These mysteries remain, inviting future generations to continue the quest for understanding. But even without final answers, the search itself is meaningful, beautiful, a worthy use of the brief time we're given in this spinning, flowing cosmos. As sleep approaches, as your consciousness prepares to enter that strange realm where time behaves differently and the normal rules of causation are suspended, remember that you are part of something magnificent. You are made of cosmic matter, animated by cosmic energy, participating in cosmic processes that span scales from the quantum to the universal. Your thoughts are quantum events amplified to classical scale. Your memories are patterns encoded in networks of neurons. Your dreams are your brain's way of processing the day's experiences, filing them away in the vast archive of your personal history. Tonight, as every night, Earth continues its patient rotation, carrying you through space at tremendous speeds you cannot feel. The moon continues its orbit, raising tides in Earth's oceans and in your own body, which is mostly water. The solar system continues its journey around the galaxy. The galaxy continues its dance with neighboring galaxies, and the entire cosmic web continues its expansion into the infinite darkness. And through it all, time carries everything forward, second by second, moment by moment, into tomorrow. But for now, in this moment, you can rest. You can let go of the need to understand everything, to solve every mystery, to answer every question. You can simply be, simply exist, simply participate in the cosmic dance without needing to know all its steps. You can trust that Earth will continue rotating, bringing you tomorrow's sunrise. You can trust that time will continue flowing, carrying you gently into the future. You can trust that the universe will continue its patient spinning and flowing, its endless dance of matter and energy, space and time. The universe spins in many directions, creating the beautiful diversity of cosmic structure. Time flows in one direction, creating the possibility of story and meaning. And you, precious and temporary, conscious and wondering, are the universe's way of perceiving its own beauty, of appreciating its own mystery, of celebrating its own existence. You're where rotation and time meet, where the cosmic becomes personal, where matter becomes aware. As you drift now towards sleep, toward that daily rehearsal for our final rest, remember that every rotation you've been part of, every moment you've experienced has been unique and will never come again. The Earth will never be in exactly this position again. The stars will never be arranged exactly as they are right now. This particular configuration of atoms and energy that is you at this moment will never be repeated. This moment is precious precisely because it is fleeting, beautiful because it is temporary, meaningful because it will pass. And so we reach the end of our contemplation, though of course there is no real ending, only transformation, only the continuation of the cosmic dance in new forms, new patterns, new arrangements of matter and energy. The questions we have explored will continue to intrigue future generations. The universe will continue its spinning and flowing long after we're gone, long after Earth itself is gone, long after the sun has died and been reborn as part of new stars, new worlds, new possibilities. But that far future doesn't diminish the importance of now, of this moment, of your experience right here at this particular intersection of space and time. You are the universe experiencing itself, a brief but brilliant flame of consciousness in the vast darkness, a moment of awareness in the eternal dance. The fact that you exist at all, that atoms can arrange themselves into patterns capable of contemplating atoms, this is the deepest mystery and the greatest miracle. So rest now, dear traveller. Let your thoughts spiral down into quietness. Let your breathing slow to match the patient rhythms of the cosmos. Let yourself drift into sleep, knowing that you are held by forces that have operated for billions of years and will continue for billions more. You are safe in the embrace of gravity, carried by Earth's rotation, flowing with time's current toward tomorrow's awakening. The universe spins in one direction, but time only flows in another, and in that beautiful asymmetry, in that cosmic complementarity, existence finds its form, consciousness finds its home, and we find ourselves, wondering and amazed, grateful participants in the most extraordinary story ever told. The story of a universe that learned to look at itself, to question its own nature, to find beauty in its own patterns, and to create meaning in the brief moments between. One rotation and the next, one heartbeat and the next, one breath and the next. Sleep well, knowing that you are part of this vast and beautiful mystery. Dream of spinning galaxies and flowing time, of cosmic dances and quantum possibilities, of the extraordinary privilege of being aware in a universe that somehow allows for awareness. And when you wake tomorrow, carried by Earth's faithful rotation into a new day, remember that you are not just in the universe but of it. Not just observing the cosmic dance, but participating in it. Not just subject to time's flow, but helping to create its meaning through your consciousness, your choices, your capacity for wonder. The universe spins, time flows, and we, marvelously and mysteriously, are here to witness it all. This is the gift, the mystery, the profound beauty of existence. This is why we look up at the stars and wonder. This is why we ask questions that may never have final answers. This is why the journey matters more than the destination, why the search matters more than the finding, why the wondering matters more than the knowing. And with that thought, with that gentle appreciation for mystery and beauty, for rotation and flow, for the cosmic and the personal, for all the questions we've explored and all the ones we haven't, we bring our journey to its close. Not an ending, but a pause. Not a conclusion, but a rest. A moment of quiet in the vast symphony of existence. A peaceful eddy in time's great river, a gentle slowing of our mental rotation as we prepare for sleep's embrace. The universe continues its dance, and we dance with it, even in our sleep, even in our dreams, always and forever part of the cosmic choreography of matter and energy, space and time, rotation and flow, being and becoming. Good night, fellow traveller. May your dreams be filled with cosmic wonders, and may you wake tomorrow with a renewed sense of awe at the magnificent mystery of existence.